The story that we are going to discuss today is one that is over 500 million years old in its age. It's a story about a violent tectonic collision that produced a slew of positive and negative events. It built the landmass of eastern Victoria and raised it from the deep ocean, but it also led to the formation of extremely powerful volcanoes, accompanied, of course, by massive earthquakes and a tsunami risk. But it also deposited vast mineral wealth. That's right, this is also a story about treasure. These same destructive events released a slew of metalliferous wealth, a byproduct of the voluminous amount of magma that would upwell towards the surface during tectonic collisions. Valuable riches in the form of gold, silver, copper, and more lie in wait, stored in huge reserves, just waiting to be tapped into and found. But these riches were hidden so well, we never even knew they existed until very recently, when their existence finally came to light with the help of modern technology, which shed light on the existence of an ancient volcanic arc that still exists in present day, known as the Stavely Arc. And it's literally lying in an area that is now the relatively flat inland region of Western Victoria. This ancient arc was hidden beneath hundreds of meters worth of sedimentary material that had accumulated and buried it over many tens of millions of years. There are some places where the material associated with these ancient explosive volcanoes are exposed in present day, but these places remain few and far between, only further adding to the mystery that had stumped Australian geologists for decades, all the way back to the days of the gold rushes in the 1850s, when geologists were everywhere and mining was an incredibly important part of everyday life. But now technology allows us to peer beneath the surface, and this is what this video is all about. This is the story of Australia's brand new mineral rush, and the massive tectonic and volcanic origin that produced it. Gold, silver, copper, lead, these are just a few of the metals that lie in massive, and I mean massive quantities, and they are just beneath the earth, right now, just waiting to be found and extracted.
Volcanic arcs are associated with some of the most violent and powerful volcanic eruptions on Earth. The volcanoes that develop here are either your typical conical formation, known as a stratovolcano, which releases eruptions that are incredibly dangerous to be around, or they can go one or more steps higher in their level of power, creating an eruption so strong it blows a stratovolcano apart and then collapses it to form gigantic calderas during the volcanic eruption, with some of these volcanic complexes being so powerful that they erupt at a supervolcanic scale, forming a caldera so large you most likely wouldn't even know you're in a caldera. Either version of these volcanoes can be so powerful that they can totally bury entire cities beneath tens to hundreds of meters worth of material in a mere matter of minutes, when they release giant pyroclastic flows or trigger violent lahars. These volcanoes are also associated with the formation of tsunami waves, occurring usually when a volcanic landslide occurs, or if the volcano is located near a large body of water during a caldera collapse. So when these arcs are active, it's a pretty turbulent area to be near. Along with the volcanic risk, you also have to deal with extremely powerful and frequent earthquakes and subsequent tsunami risks. But along with this danger exists valuable riches just waiting to be found. These arcs are associated with the release of extremely precious metals, with gold, silver, lead, and copper being a few of the metals that occur en masse when these events occur. And these deposits usually accumulate for millions or tens of millions of years, leaving layer after layer of extremely metal-enriched deposits that would make you rich overnight. But in order to find these, you have to know the different ways that these valuable and much sought after metals accumulate, and we will cover all of this later on.
A volcanic arc is also known as a magmatic arc, And this giant belt of volcanoes form above a tectonic plate when another plate collides and subsequently subducts beneath it.
Present-day examples of these types of volcanic arcs can be found within the Japanese archipelago, the Sunda Arc in Indonesia, or within the Andes. The volcanic arc we are going to cover today formed in exactly the same way as all of these examples, but it was more closely related to the Andes in the chemistry of its magma and in the topography of the land, meaning the place it occurred at more closely resembles the Andes in its biomes and overall layout, with gigantic mountain ranges stretching high into the sky, with hundreds of massive volcanoes and volcanic calderas dotted everywhere throughout the land. Victoria is located in the southeastern portion of Australia. It's known for containing some of the richest goldfields to exist on our planet, and the geology here is convoluted, layered, and beyond complicated. The massive sequence of effusive eruptions produced wave after wave of lava flows, and occurred at over 400 different locations all throughout the state, starting sometime around 2 million years ago, as Victoria drifted north over a hotspot that had been causing inland volcanic eruptions to occur in Australia since northern Queensland first drifted over it, and in time, the hotspot slowly moved south all the way to Victoria and beyond, lying somewhere beneath the Bering Strait in present day. The vast majority of the state is covered in basalt or is located beneath large amounts of sedimentary material, meaning vast amounts of wealth lie beneath the soil, but the only way to find and extract it is by understanding how this complicated geological puzzle that is Victoria formed, so that we can extrapolate this understanding towards deciphering what riches lie in wait to be discovered. The only issue is Victoria is unbelievably complex. Like really, it's an absolute mind. It's only recently that it's begun to be understood purely because of modern day technology and the ability to measure deep within the earth. As a result of this new ability, Victoria has some of the highest quality magnetic and gravity data available in the world from the recent and thorough in-depth studies that have taken place here. Magnetics allow us to peer down to about 30 kilometers beneath the surface of the Earth, and with gravity, you can see even deeper than this. And this data, combined with drill cores, can penetrate deep into the Earth to take a sample of the rocks and investigate what minerals make up the layers without having to physically investigate it by constructing a mine shaft like they would back in the old days, and this unlocks the ability to prospect on an entirely new scale. So these techniques, along with other recent technology, have finally begun to unravel the complicated puzzle that is Victoria, and that has led to some truly monumental discoveries. Take this gold mine for example. It was discovered in an area where gold was first discovered in 1894, and it was then mined until 1903. But the old miners, who were amazing at what they did by the way, completely missed this unbelievably gold-enriched location. But how? Well, it was located beneath basalt that was erupted from the more recent volcanic eruptions, and was only discovered using modern techniques. It was completely hidden from the miners, and they had no way of knowing it existed there. But at only 15 meters beneath the surface, underneath this basalt, lay a vein of quartz so gold enriched that it yields 1429 grams per ton, which is unbelievable. That means this mine earns 115,277 Australian dollars per ton of ore crushed, and they've mined over 3.5 million ounces of gold since the commencement of the current operation in 2015. This is one example of what recent technology is allowing us to discover, and the next discovery might be a Fosterville times 1000 or more, because this isn't just one spot that's been discovered. It has unlocked the potential for an unbelievably vast amount of mineral wealth located underneath a vast stretch of land. And this is where our story drifts back to the magmatic arc. Victoria formed within the past 550 million years. It was originally just a deep ocean that lay off the east coast of Gondwana. Tectonic collision occurred as the ancient Paleo-Pacific tectonic plate collided with the continental plate of Gondwanaland, and the heavy oceanic Paleo-Pacific plate subducted beneath the lighter continental plate. This collision led to the formation of a gigantic volcanic arc, known today as the Stavely Arc. It stretched from the shores of ancient Gondwanaland, which is now in western Victoria, all the way south and into Antarctica, which at this point in time was connected to Victoria, so a good part of this volcanic arc is also located somewhere in present-day Antarctica too. This entire magmatic arc lay hidden from the naked eye, and was completely undetected as it sat buried beneath vast layers of sedimentary material which had buried it in the past 500 million years since it finally became extinct. But when you look at it through the magnetics, suddenly something amazing pops up. As you can see, this completely changes our ability to see things. Suddenly, the large stretch of sedimentary plains and desert have become invisible, and what we now see are the remains of the now dead volcanic arc that roared to life vigorously 511 million years ago, but that most likely originally began life around 522 million years ago. This volcanic arc has changed dramatically though. It looks nothing like it would have when it existed. There have been several tectonic events that occurred here post 500 million years ago, and these collisions have folded, buckled, warped, and moved the volcanic arc all over the place. The orogeny that caused this buckling is most likely what killed the volcanic system to begin with, by thickening the crust and choking off the ability for magma to easily rise. And the multiple orogenies that would occur would lead to 19 present-day belts that exist of both volcanic and intrusive rocks. But 500 million years ago, they would have existed as only 4 large volcanic belts, before becoming twisted and rotated along with the present-day marvel known as the Grampians. 440 million years ago, the deep ocean retreated eastwards, and mountains began to be built, raising another large portion of Victoria out of the deep ocean. And it was during this time that the Grampian strata was laid down, burying the rocks that made up the Stavely magmatic arc, before becoming tilted and folded 405 million years ago, in an event that also affected the much older rocks that made up the Stavely magmatic arc. After this event, this part of the Earth became so stable that it preserved the upper crustal levels of these 500 million year old rocks, leading to them existing in present day, rather than them having been exposed and eroded away. This is extremely unique and is quite a special occurrence. So the reason why this discovery of the Stavely Arc is so significant, among many other reasons, is because the Andes are known for having some of the richest copper porphyry deposits in the world. And along with that, the Andes also has vast quantities of other valuable metals such as gold. It is a place of immense tectonic activity in the form of earthquakes, and there exists some of the strongest and most explosive volcanoes along the entire Andean mountain range, from your standard Plinian volcano all the way up to supervolcanoes that are active in present day. So 500 million years ago, if you were to stand at this location and look out to the east, you would see nothing but a vast stretch of ocean that would be the Paleo-Pacific Ocean. And if you looked west, you would see massive rugged mountains similar to the Andes, only located in present-day Victoria. The one difference is that the Andes is tectonically active in present day, whereas this volcanic arc is long dead. This is huge because the most valuable phase of mineral injection is in the final pulses that are released by the magmatic system as it is about to die. This final burst of fluidic wealth deposits the largest and the most richest layer of gold, silver, copper, lead, tin, etc. The reason this occurs is because as subduction ends, it's changed from the arc being shortened and squashed to suddenly being released into extension again. The final release of this confining pressure results in a massive pulse of magmatism that brings metalliferous granite and porphyries towards the surface. So somewhere underneath the deserts and sedimentary plains of Australia lies an incredible amount of vast mineral wealth that might be worth billions upon billions of dollars or more in value. And these riches lay not only in the volcanic rock that was released, but also in a much wider stretch of land, with nearby sedimentary rocks from this date, 500 million years ago, also containing vast amounts of these riches. But how could sedimentary rocks contain them? And how do bursts of pure gold and other valuable metal deposits form? One way is within what is known as volcanic massive sulfide deposits, or VHMS deposits for short. These form directly on the seafloor in an area where ocean crust is being stretched away from the subduction zone. When highly active, these deposits can be associated with what is known as a black smoker environment, which are essentially chimneys located directly on the ocean floor that are constructed out of valuable metals that increasingly accumulate with time as more acidic fluid continues to upwell through the ocean crust. When the Paleo-Pacific Ocean was subducting beneath Australia, the section that was magmatic occurred mostly in the oceans near the continental land of Gondwana. It started deep within the ocean and released wave after wave of VHMS deposits during its life. Black smoker environments scatter precious metals all over the place, leading to them accumulating on nearby sedimentary material, where it would then become intertwined within it. So the area of land that could be enriched is vast beyond words, and these metals all tend to accumulate with other metals of the same type because of their varying specific gravity. So when one section is discovered, vast amounts of it lie in one area, making it easier to extract. But there's a second way that these valuable metals are deposited, and that occurs with a phenomenon known as porphyry deposits, which itself includes epithermal deposits. Porphyry deposits are the final burst that I mentioned earlier. They are intrusive deposits and they form at depths of 1 to 6 kilometers beneath the surface. As magma cools, metals begin to precipitate out of the highly pressurized and hot hydrothermal fluids, and they begin to enrich the nearby rocks around the magma chamber, creating what can only be described as a mineral-rich halo around the slowly cooling and solidifying magma chamber. As temperatures drop, metals begin to separate out one at a time, beginning with copper, followed by molybdenum and gold, then silver, lead, and zinc, creating zonations of enriched areas with different metals. As the magma chamber cools, the top of it crystallizes, resulting in the release of water and other volatiles. These hydrothermal fluids carry metals from the top and exterior of the magma chamber into the surrounding rocks as it exploits cracks and voids above it. As these metal-rich brines ascend and the pressure decreases, they eventually reach their boiling point, at which time metals begin to drop out of solution. Again, like before, copper comes first, followed by molybdenum and gold, then silver, lead, and zinc, as we get further away from the heat source. This process creates epithermal deposits above the magma chamber, which form in the cracks in the surrounding rock as veins and along weak sedimentary plains as sills, which can then be exposed due to erosion or can still remain preserved. In this case, they are preserved and they lay out there right now, hidden beneath the sedimentary basins of the Murray and Otway Basin. So this final porphyry phase occurred at the 500 million year mark, when this volcanic system released its final metal-rich pulse of metalliferous porphyry deposits and granites that intruded into the upturned fault slices of the dying Stavely Arc, with epithermal and VHMS deposits located across an incredible stretch of flat, ordinary, and deceivingly boring land, with sedimentary rocks also containing it, which only further increases the search radius, meaning there's not only a brand new gold rush that's about to occur at a modern day level in Victoria, but there's also a potential for a copper rush among other metals, with billions upon billions of dollars in rock form laying out there right now just waiting to be claimed. It's just been discovered, so it won't be long until the riches that are lying out there in wait are found and extracted. So in present day, the fault known as the Moistened Fault marks the line where the ancient continent of Gondwanaland met the subducting Paleo-Pacific tectonic plate, which is something that I find fascinating, and this is why I love geology. This entire story is just incredible in my eyes, and the riches it left behind to be claimed are just mind-blowing to me. It astonishes me to think that at this point 500 million years ago, to my west was the vast supercontinent of Gondwanaland, and to the east was a vast ocean that stretched out for hundreds to thousands of kilometers into the distance, and right at the edge of the continental plate lay a vast chain of explosive volcanoes that would lay down vast mineral wealth, and whose image still exists to be seen in present day with magnetics. This is the closest I can get to a stratovolcano in my home state, and I'll take it.
Volcanic arcs are the byproduct of subduction zones around the world. They host violent explosive volcanic eruptions, but along with this they also deposit vast mineral wealth into the fractured bedrock, with many volcanic arcs containing significant quantities of gold, copper, silver, lead, and other metals. The reason volcanic arcs form is due to the subducting plate. When an oceanic plate collides and descends beneath a continental plate, water is introduced into the mantle in two ways: by the subducting slab dragging oceanic water down with it, and by the release of water from water-saturated rocks when they reach a specific depth, where the heat and pressure force them to undergo metamorphosis. When water is introduced into the mantle, it lowers the melting point and induces partial melt as a result. Minerals become sequestered and concentrated. They are sweated out, so to speak, from the subducting slab, and the magma and fluids that are released begin to travel upwards due to buoyancy, utilizing the faults and fractures that subduction inevitably creates to ascend where they can become deposited into the bedrock. This is one of the few ways that volcanic arcs deposit minerals into the land. In northern Queensland, an ancient volcanic arc that formed 298 million years ago during the early Permian exists in the northern part of the Bowen Basin. These volcanics were formed during a subduction event, and they outcrop in various areas. We have a high degree of mineralization in some of these areas, with copper, silver, and gold occurrences. Other areas, however, are completely devoid of mineralization. On geological maps, the Lizzie Creek volcanic group is represented by a light blue color. Its formation began when the oceanic Paleo-Pacific tectonic plate subducted beneath the continental Indo-Australian plate, giving birth to volcanoes and major earthquakes. These volcanoes were tremendously explosive in their magnitude, with the release of rhyolite and rhyodacite being pronounced. And we have the later formation of a back arc basin in an area where the land was stretched. This is known as the Bowen Basin in present day. This basin deformed a Lizzie Creek volcanic arc in certain areas, and we have other intermingling volcanics that joined the Lizzie Creek in erupting during the early Permian, and it overlaid it in certain parts, such as the Mount Toussaint volcanics and the Strathbogie trachyte. We also have a group called the Mount Wickham rhyolite on the westernmost border of the arc, where the aforementioned later deformation occurred. It appears as though the stretching of the land occurred in the later part of the Permian, after this volcanic arc had existed for over 40 million years, spewing out explosive and effusive eruptions. What's really cool is, under magnetics, we can see massive dikes or veins that were emplaced by hydrothermal waters and by magmatic processes. Look at the linear lines that exist so abundantly throughout the region on magnetics. It's possible that these dikes or veins might contain high mineralization in areas and yield an abundance of gold, silver, copper, and other commodities. The red lines that you see on the geological map represent them, and they are numerous and quite widespread in places. Right alongside the Lizzie Creek volcanic arc are numerous major intrusive rocks like the Thunderbolt granite. This would have been the fuel source for the volcanoes in the Lizzie Creek complex, and they have been uplifted to the surface. In present day, the mineralization that occurred in the Lizzie Creek volcanic arc occurs most abundantly in the Mount Carlton area. It's only now that we're really beginning to drill into the earth to see if any significant copper or gold deposits exist. Significant is the key word here. There are former prospects that uncovered gold, silver, and copper in the region, but they have been small scale and the yields haven't been great enough for small scale miners. This is typical of volcanically emplaced gold, which, as opposed to orogenic gold, doesn't contain the high yields one might expect or hope to see. But volcanic gold is normally concentrated in certain areas, due to a process known as magmatic differentiation. Magmatic differentiation occurs as magma rises through the Earth's crust. As it does, different minerals crystallize out of the magma at different temperatures. The result is a concentration of valuable minerals like gold, copper, and silver in certain places. This can lead to extremely high yields if the right place is drilled that contains a deposit that was emplaced by magmatic differentiation. The result is a bounty of gold or other metals. Open pit mines are often used to extract these minerals. The Lizzie Creek Volcanic Arc is one of many examples of these kinds of volcanic remnants. Ancient volcanic arcs are scattered all over Australia, speaking to the many different tectonic events the country has undergone throughout time. So this is the story of a once mighty volcanic arc that eventually died off and left behind the remnants and riches from the time when it roared to life, to the point where the magma finally cooled. Thanks for watching.
One thing that I hadn't done, much to my astonishment, was explore the islands between Tasmania and Victoria using magnetics. I know, right? What on earth have I been doing with my f***ing life? I've been squandering time. But for some reason, this morning it struck me that I hadn't done it yet. So I downloaded the magnetics layer and activated it, and voila, there it was, like, hey dude, you found me. And indeed, I have found you, Mr. Cheeky Volcanic Arc. No arcs can hide from the scrutinizing gaze of Mr. OzGeo. But now that we've illuminated this undoubtedly very ancient volcanic arc, we'll try to unravel the geological narrative behind it. To my knowledge, this hasn't been done yet. I've combed through the scientific literature. My eyes are as red as Cheech's right now from staring at the screen all morning. Dozens of articles, hundreds of pages from our good friend et al. And guess what I found? Nothing. Not a single mention of this volcanic arc. And nothing even came close. Am I surprised? No. I've said this many times before, Australia is underexplored. Geologically, it's still a land of new discoveries, so either this hasn't been discovered or it's been seen but not deemed worthy of investigation for some reason, or something else. But this right here, without a shadow of a doubt, is an ancient volcanic arc. I know this because I've discovered numerous previously undocumented arcs using geophysical methods during my time on this magnificent Earth. And as is the new usual, this video has also been turned into an article which you can read on OzGeographics.com. So I won't claim to be the first to discover it or anything like that, but I found an ancient volcanic arc in the ocean near Tasmania, and I did all of this while taking care of nature's call. Ah, the wonders of the 21st century. About 1.6 billion years ago, Tasmania was born. We now refer to the microcontinent that encompasses Tasmania as Van Dieland. It's more accurate to say Van Dieland was born, and it did its own thing for about 1.1 billion years, just drifting around the globe, colliding with places, rifting, accreting, you know, all that good stuff. Around 430 million years ago, it slammed into Western Victoria, causing a continent-to-continent collision, and approximately 360 million years ago, the system finally shut down, and it's been part of Australia ever since. But this volcanic arc is much older than Eastern Australia. It's definitely twice its age. This is a very ancient subduction zone. In fact, it appears that King Island's origin is actually one that sits atop a series of volcanic arcs, but its oldest rocks are the metamorphosed oceanic sediments from as old as 1.6 billion years ago, proving that King Island has always existed alongside Tasmania since the very beginning. But as you can see, we've got this one off the coast, and we have another arc here in the southwest. It's primarily buried by recent erosion-related sediments, except for a few key areas where it outcrops in the form of different volcanic rocks, ranging from intrusives to ancient extrusives. And one can tell something significant happened here simply by looking at the complex faulting that's occurred here. But whatever happened here did so about 600 million years after Van Dieland was born. And it may seem like nothing but a small island, but this place has seen some things. From the evolution of complex life to the first plants and beyond. It's witnessed every extinction event, and its inception might have been just as destructive. But now it just sits here. No name assigned to it, to my knowledge, lying buried beneath the waves of the Bass Strait, and beneath the sediments on King Island, with some outcrops here and there that hint at the true origin of this land.
It's very possible that Aboriginal eyes gazed upon the now submerged volcanic arc before the waters here rose to inundate the land. Now the rocks here have all been dated, and we have areas where rocks associated with the arc are outcropping. So as you can see, something happened between 1 billion and 540-ish million years ago. I'm still trying to ascertain what exactly happened, and it's quite complicated to do so when you go back beyond, let's say 600 million years. But so far, it has to be one of two things. Either King Island was a back arc basin, that being the area behind the volcanic arc where the land experiences a zone of rifting, leading to the formation of highly explosive volcanoes and supervolcanoes, or, and my bet is on this one, this has experienced a rift event recently as part of the Port Phillip Sunklands, meaning King Island may be where it ends. I made a video on this a few days ago. Basically, I formulated a hypothesis based on some solid evidence that the recent rift zone that occurred and that stretched Melbourne apart so significantly within the past 30 million years did so as a result of the recent continent-to-continent collision that's occurring in New Zealand, which I postulate has effectively stretched the land apart. And based on magnetics, it appears the rift may venture as far south as King Island, meaning this area of blue is more than likely a recent occurrence. It's likely that before 100 million years ago, this entire area was comprised of relatively tight-spaced volcanic arcs that have now been separated, showing this V-like line over here. Something wacky is going on here, and I'm going to guess now that the models of Victoria in 20 years will be completely different from what they are now if it's discovered that this rift event is still active, which I honestly really do think it is. Now, the part of the island with the most exposed section of the arc would be the northwestern part. Here we have ancient granites ranging from 545 million years to a billion years old. Now, interestingly enough, we have an amphibolite metamorphic complex here. Without going too much into it, it's one of the many classifications that list rocks based on the pressure and temperature grade they've been subjected to during past metamorphic events. Amphibolite is more often associated with continent-to-continent collisions than it is with subduction events. However, they can still occur during subduction. It's possible that this occurred when Van Dieland collided with Australia, long after the arcs had gone extinct. Either way, it shows this land went through a marked degree of compression and metamorphic alterations as a result of numerous different tectonic events experienced over time. In the middle of the island, we have thick-bedded quartzose siltstone from as old as 1.6 billion years ago, up to around that same number of 545 million years, suggesting this area has always been some kind of depositional feature like a basin or deep ravine, possibly an ancient rift zone. Now, things get interesting again around the 400 million year mark. Van Dieland collided into Australia 430 million years ago, and we can see that it's restarted the magmatism here. We have magmatic intrusions that occurred. One did so in the northeast, emplacing this monzogranite and granodiorite layer. You can see it occurred around the time of the collision, and existed throughout right up until the end. This collision was quite intense though, so it's no surprise that intrusions continued long after it had ceased, and this is evident by the porphyritic monzogranite that continued to intrude here in the southeast from 354 to 298 million years ago. Now, I don't know what type of exploration has been conducted on King Island, but I'm actually quite surprised that no gold discoveries have been made, and I'd bet $1 million if you got me on that island and gave me permission to dig, I'd fucking find gold. 100%. But the metals we do have right now are indicative of intrusive and volcanic arcs like tungsten. So I can tell you right now, King Island has had a tumultuous history, and there'd undoubtedly be valuable minerals within the soils, and the surrounding, now submerged land, which is more than likely rich with alluvial gold among other metals as a byproduct of the immense tectonic history that has unfolded here. This and the associated arcs are giant. Their size shows it was a major system, but this is just one of many anomalies I've come across this morning. In fact, there's an amazing geological story that lies obscured beneath the waves of the Bass Strait, and that is now only visible due to magnetics. Let me know if you like this type of video where we use magnetics to attempt to ascertain what geological processes have occurred to underexplored lands that lack any study at all as it pertains to the arc or any other geological feature. If you'd like to see more, let me know by leaving a like and/or a comment, as I'd love to turn this into a series. This is the part of geology that I absolutely love and am deeply passionate about. So I hope you enjoyed this video that delved into the ancient volcanic arc that roared ferociously in the once barren and lifeless soils of primordial Tasmania, Van Dieland. And here they still stand, a testament to the immense tectonic and volcanic forces that shape our planet. Thanks for watching. If you watched a video I made 2 days ago, you'll remember we had quite an exciting discussion about the mineralization of King Island. I even went off script and made a bold claim. I bet $1 million that we'd find gold there if given permission to dig. Well, today's video will be a thrilling follow-up to that claim, and not a single shovel needed to be plunged. A subscriber sent me a link to an article from the 1870s discovered in the Trove archives, where a child found gold on King Island. Thank you so much to the sub who did that, by the way, I really do appreciate it. And it wasn't just a speck or two, it was determined sufficient in amount to render it payable. The discovery didn't really raise too many eyebrows at the time, as this was 20 years into the gold rush of Victoria and no one was keen to leave the state known for the largest gold nuggets in the world to go to some random island that may or may not have a lot of payable gold on it. The purpose of today's video is to demonstrate how a background in geology can help you understand the mineralogy of a place without ever setting foot on it. And all of this is attainable with a little bit of self-study. It's a fascinating field that allows us to read the Earth's history and predict its hidden treasures. So without further ado, let's look into this discovery, where it was made, the geological processes that formed it, and how I knew gold was here to begin with. Firstly, you'll always find gold in some form where there have been tectonic collisions. This is due to hydrothermal fluids and the emplacement of mineral-rich waters that percolate and solidify into quartz within the many faults and fractures in the bedrock of the slowly deforming land. In the last video on King Island, we discussed a tungsten mine, but upon further reading, I discovered that tin mines have also operated there. Tin is typically found in cassiterite, associated with granitic magmas. Unsurprisingly, tin is heavily associated with volcanic arcs. And if you recall, we discovered a volcanic arc on King Island, with granite outcropping as the predominant volcanic rock here. It's worth noting it's not exactly clear whether or not this granite was outcropping pre-30 million years ago. It's possible its exposure to the surface was due to the proposed rift event that I spoke about in the previous video. The volcanic arcs may have been torn apart into the V-shape that I showed on the infographics in that video, unveiling a granitic basement. This granite is the magma chamber that fed the arc. Only they solidified beneath the earth when this system finally shut down, and they could never accumulate enough pressure to erupt onto the surface. So here they are, ancients lying frozen in time. Now let's talk about the gold. It was first discovered on the northernmost tip of the island. This isn't surprising as the ancient granite has been exposed in a good section of it. This is the bedrock layer, so any eroded gold would sit right on top of this granitic layer, and indeed that was the case. But here's where things get even more interesting. I postulate there are two forms of gold on King Island, those of volcanic origin and those shot up through hydrothermal processes. When I say hydrothermal, I basically mean the typical quartz veins that we associate gold with. The proper term for this type of deposition is known as orogenic gold deposits. These veins were emplaced into the bedrock during the subduction events and the subsequent mountain building episodes. On the other hand, volcanic gold is tiny to microscopic, but present, sometimes in payable quantities. It tends to be lower yielding though, with ore generally yielding a few grams to the ton of crushed ore versus the half an ounce to an ounce one would hope to obtain from hydrothermal veins. However, this is only sometimes true, and highly concentrated volcanic gold deposits exist, generally as a result of re-enrichment processes. Gold is usually found alongside a host of other metals in volcanic ore, such as copper, silver, lead, etc. Hydrothermal veins may have a mixture too, but their overall composition is less diverse and more focused, so to speak. There have been 2 gold-bearing veins discovered on King Island that I've read about. I've only found 3 articles on this subject, but prospecting licenses were indeed taken out. It's yet to be known what work was done though. There's both alluvial and hard rock work that's been conducted, but I'm unsure of the extent, and I'd only really be able to ascertain it if I personally stepped foot on King Island. The first gold-bearing lode was the one discovered with the initial discovery. A boy found gold while out kangarooing. The reef itself was 12 feet or 3.6 meters thick. and it ran quite a distance, venturing out into the sea and beyond reach after that point. We'd also have some very interesting mineralogy occurring here because of the limestone hills that make up many sections of King Island. Carbonate gossans are strange and fascinating. They're a subject I have yet to have the opportunity to explore much because of their lack of existence in the areas that I've lived. I might have to go to King Island after all, because carbonates can host a variety of mineral deposits. Lead, zinc, copper, gold, iron, fluorite, phosphite, barite, rare earth elements, and even radioactive minerals, which I'd prefer to stay the hell away from. In the article, the texture of the gold is mentioned. It's said to be flat and very worn, appearing as though it had been conveyed a considerable distance. This line is sticking out to me like a sore thumb, and I'm going to ponder it in the coming days to understand it more. I know that this gold is very ancient and was deposited eons ago, but this description of it appearing to have been conveyed a considerable distance seems to be something important to me that I need to keep in mind for a later date to better understand the geological history of King Island. The fellas who made this discovery took 3 weeks to find their first speck of gold, and as usual, they did so right as they were about to leave. The typical prospector's luck. But I hope this piques the interest of prospectors out there to attempt to understand more about geology, because it really is the pinnacle for discovering mineral deposits, among so many other things. Geology has single-handedly changed and enriched my life in so many ways, from altering how I view the world to helping me make discoveries or have an eye for identifying potential findings when they're present. In a coming episode, I'm going to introduce you to something I like to call hidden volcanoes, of which I've found a few on King Island. I hope you've enjoyed this exploration of King Island's geological history and the fascinating world of mineral deposits here. Remember, every rock has a story to tell. You can uncover these stories and make incredible discoveries with some knowledge and curiosity. You'd be amazed at how many people walk past seemingly ordinary, boring looking rocks, only for some nerd like me to come along, pick it up, and stare at it intently for an uncomfortably long duration before deducing potential value and making a discovery. Recent history is filled with stories of discoveries that were made this way, and I've personally made at least 2 discoveries in my lifetime in highly explored areas that, for whatever reason, overlooked something that stuck out to me. So keep exploring, folks, and remain curious and hungry for knowledge. Discovery is still out there for those determined enough to seek it, even if it's done in a toilet stall on your phone whilst going number 2. It's still a discovery nonetheless, and when you hit flush, you can do so with added satisfaction. Thanks for watching. Today we're diving deep into a fascinating geological phenomenon that I've come to call shadow volcanoes. This isn't a term you'll find in a textbook, it's one I've coined to describe a curious and largely unnoticed aspect of the geology of Eastern Australia, including Victoria and Tasmania, and the islands in between. So let's dive right in and demystify what these shadow volcanoes are all about. Our story begins around 85 million years ago, when the continents of Australia and the newly forming continent of Zealandia, where New Zealand lies, were separating from one another, a geological event that gave rise to the Tasman Sea. This separation, or rifting, as it's called, caused weaknesses in the Earth's crust, creating pathways for magma to upwell from deep within the Earth and erupt onto the surface. This resulted in numerous volcanic eruptions, particularly in what is now Victoria, which spewed copious amounts of fast-flowing lava onto the land, creating what we now call the older volcanics. Fast forward to roughly 30 million years ago, Australia is moving north ever more. It slowly moves over a so-called hotspot, an area within the Earth's mantle from which an abnormal amount of magma rises. This hotspot resulted in a series of volcanic eruptions. Much like a string of dominoes falling one after another, these eruptions began in northern Queensland, and over millions of years, progressively moved southwards as Australia continued its journey northwards over it, resulting in volcanic activity in New South Wales, Victoria, South Australia, and even all the way down as far as King Island and Tasmania. Now, it's essential to understand the type of lava these volcanoes produce. They were mostly spewing out a kind of rock called basalt. Compared to other volcanic rocks high in silica, such as andesite and granite, basalt isn't as good at resisting erosion. Over millions of years, the relentless forces of wind, water, and ice have worn away these basaltic landscapes, causing significant erosion. In some cases, the volcanic vents didn't release enough lava to form a large permanent structure, so they eroded away quicker. This is where we get to the concept of shadow volcanoes. Essentially, we're talking about places where there were volcanic eruptions in the past, but they aren't listed as occurring on any geological maps. In fact, their entire existence is strangely omitted, which I assume is due to some kind of misinterpretation, possibly attributed to the significant erosion that's occurred in some places or the lack of voluminous flows being released in others. So yeah, as a result, they're not listed in any of the available geological maps, much to my frustration and constant annoyance. I can't even begin to tell you how many areas I've studied that would list the land as being purely sedimentary, only for me to drive there and shout at the fact that there are literally dozens of tiny stubs of highly eroded volcanic vents everywhere. My mates know full well about my annoyance regarding this subject. These little guys were so hidden that it's possible they've remained obscured from geologists themselves. And well, since they're shadows of their former selves, and since they appear to be a volcanic version of a ghost, so to speak, I've given them the term shadow volcanoes. So how do we know these shadow volcanoes exist if we can't see many of them? Well, this is where the science of geophysics comes into play. By studying the magnetic properties of rocks in a given area, we can identify the telltale signs of past volcanic activity, even if the physical evidence has largely been eroded away, and this is purely because basalt is rich in iron, and it pops out like a sore thumb amongst the surrounding sediments and granites. And once we know where to look, then we can go out into the field and search for any remaining physical evidence of the volcano, even if it's just a small stub or rounded hill, which it usually is. And as you can tell, magnetics is no joke. Some of these volcanoes release so much lava that you can make out the conical shape on the magnetics themselves. But others, well, they're cheeky. They hide very well. Check this out. This is the Ringwood area east of Melbourne, right next to the Warrandyte goldfields. I went to my mate's house last week because he wanted me to dig his yard and see if he had gold. I checked geological maps before I left, and as you can see, the Andersons Creek layer is listed here as being purely sedimentary, compared to this layer right here, which is an example of where basalt was identified. The Greensboro basalt layer erupted around 23 million years ago when Melbourne's rift zone was at its most active. So I drive to my mate's place and what do I see? Basalt everywhere. Everywhere! Basalt of varying kinds too, and of varying ages, so we have multi-phase eruptive byproducts here, none of which are listed. This could be basalt from 500 million years ago when Victoria was first born, 20 million years ago when the rift occurred, or related to the hotspot and released within the past 7 million years. So naturally I step out of my car, greet my mate, and immediately crack it over his fence, which is constructed out of the very basalt that was apparently never erupted here, according to geological maps. And to further rub salt in the wound, all of his neighbours' fences were constructed from the very same basalt. So I jump on magnetics, and it doesn't appear like much, true? This could be more impressive compared to that magnetics image I showed you of that massive conical volcano. But let me show you something. The cheekiness of the shadow volcanism is about to be unveiled for all to see. Because these, yes these are all freaking volcanoes. They're either small eruptive vents of varying ages or very old medium-sized conical structures that have been highly eroded. And look at them all, it's sickening. Now, all of this may seem like a minor detail, but it's a significant issue for anyone studying or exploring the geology of Eastern Australia. I've personally encountered this situation numerous times during my career. I'd start by studying a geological map of a particular area, then when I got there in person, I found that the real-world landscape was dominated by highly eroded basaltic rock, not the other types of rocks indicated on the map, meaning I now had to dig through what could be many feet, or in the worst case scenario, many meters worth of highly eroded basaltic overburden. The implications of this can be profound. For instance, if you're searching for gold deposits, it's important to know whether the landscape you're exploring has experienced volcanic activity in the past. When basalt is in its lava state, it readily flows in a stream-like manner, covering up the older rocks that contain the gold that I am seeking, making them harder to find and more work to reach. These eruptions would often disrupt and redirect ancient river courses too, affecting where gold might be found. And when multiple eruptions occur over a long period of time, temporary streams that form post-eruption get created, sediment accumulates for a period of time, Then another eruption occurs and a new river takes over and it changes course again, meaning multiple placer deposits could exist in the location as a result of the volcanic component, and I need to know that. Like, you know, far out. This issue of shadow volcanoes is particularly relevant in mineral-rich areas such as Malagal and certain regions around the Grampians area. However, the most striking recent example I found was at King Island. Despite the clear evidence of volcanic activity on the island, as indicated by magnetic data, the official geological map of the island does not even include or even state the existence of any recent volcanic rocks occurring here. This discrepancy underlies the importance of acknowledging the existence of shadow volcanoes in regions like Victoria. Their presence can significantly affect the approach to geological exploration and research in these areas. It's a lesson in how our understanding of the Earth continually evolves and how new concepts like shadow volcanoes can dramatically alter our interpretation of the landscape around us. By shedding light on these shadow volcanoes, we can further our understanding and appreciation of our planet's complex and ever-evolving story. So, the next time you look at an unimpressive hill, you could be looking at a cheeky shadow volcano hiding from plain sight. Thanks for watching.